All right, class. So Unit 3 has two parts. The first part are the discrete probability distributions. We covered the binomial and the geometric distribution, and that goes through assignment 1. And then assignment 2 is on the normal distribution. So this is chapter 5, normal probability distributions. And this chapter has 5 parts, and we do cover the material from all 5 of them. So there's an introduction to the normal distribution and the standard normal distribution, and that covers numbers 1 through 4 in your homework. And then there is the finding probabilities using the normal distribution, and that's numbers 5 and 6. And then finding values for the normal distribution. So this is giving the probability, finding the values, and that section, numbers 7 and 9 in your homework. And then sampling distributions and the central limit theorem, and that covers number 10 and 11 from your homework. And the last section is using a normal approximation to a binomial distribution, and that covers your homework number 12. Okay, so we're going to start with 5.1, which is an introduction to normal distributions. So first of all, the binomial and the geometric distributions are discrete distributions. And what that means is the random variable x can only take on countable values because it's counting the number of successes in n independent trials. So it is a count. That's for the binomial. And the geometric is the trial on which the first success occurs. So that's also something that we can count. Okay. So what's a little different about the normal distribution is this is a continuous random variable, which means that the variable x has an infinite number of possible values, and it can be represented by an interval on a number line. So one example is the hours spent studying a day. So again, weights, time, volumes of things, those are all continuous. Anything that represents those would be a continuous random variable. So the time spent studying can be any number, it can be fractional, any number between 0 and 24. So this is a continuous probability distribution, and a continuous probability distribution is a probability distribution for a continuous random variable. So that's the difference between a discrete probability distribution. It's that a discrete probability distribution is a probability distribution for a discrete variable, and a continuous probability distribution is a distribution for a continuous random variable. So again, here x would represent the number of hours spent studying in a day, and that is continuous, so we need to use a continuous distribution. So you guys have all seen the normal distribution before. It is a continuous probability distribution for a random variable x, and probably the most important continuous probability distribution in statistics. And the graph of the normal distribution is called a normal curve. So this is where I said you guys have seen this before. It's a bell-shaped curve. Okay, so what happens with this, you'll notice it is symmetric. And because it's symmetric, the mean, median, and mode are all equal. So it's showing us here at this highest point, this is the mean. This is also the median, and this is also the mode. So mean, median, and mode are all equal. It's bell-shaped and symmetric about the mean. The total area under the curve is equal to 1. And the area under the curve represents the probability. Okay, so the normal curve approaches but never touches the x-axis. So this will basically extend on forever and never touch the x-axis. So it definitely doesn't cross it. So as it extends further and further away from the mean in either direction, as it goes out here, it gets closer and closer to the x-axis here and closer here as well. Okay, some properties of a normal distribution between sigma minus 0 and, between mu minus sigma and mu plus sigma which is here in the center. So let me actually start with here. So this is the mean, okay? So when we look at a normal distribution, there are two parameters that we need in order to draw this curve. I need to know what the mean is, and the mean will be in the middle of the curve. And I need to know what the standard deviation is, because that tells me how far apart these 2 points are. Because here's the mean minus 1 standard deviation, and here's the mean plus 1 standard deviation. So this is the mean minus 1 standard deviation, the mean minus 2 standard deviations, the mean minus 3 standard deviations, the mean plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations. So if my mean is 100 and my standard deviation is 10, this would be 100, 110, 120, 130. This would be 90, 80, 70, okay? So we need two numbers to draw the curve, the mean and the standard deviation. The graph, so the graph curves upward to the left of mu minus sigma and to the right of mu plus sigma. So what that's saying is these 2 points on the curve, these are the inflection points. And inflection points are where a curve switches from being concave up to concave down, or vice versa. So anytime it changes, the concavity changes. That's where the inflection point occurs. And the way that I like to think about it is, imagine that this creates like a cup. Okay, so when I look between these two inflection points, the water will run off. Okay, and when I look between these two inflection points, if I kept going and combining this like this, this would hold water. So when it would hold water, then it is concave up. And when the water would run out, this is concave down. So this is concave up, and then this is concave down, and then this is concave up again. So that's what it's saying. It changes from concave up to concave down, and then back to up. So these are our inflection points. That's where that change actually occurs. Right? And then again, like I said, this tells us kind of how wide that this is. So the bigger that our sigma is, the more flattened out our curve becomes. So here it's showing us some examples, different means and standard deviations, and what happens to the curve. So here's a curve. Our mean is 3.5 and our standard deviation is 1.5, which means my inflection points are going to be at 3.5 minus 1.5, which is 2, and 3.5 plus 1.5, which is 5. So here are my inflection points at 2 and 5. And you can see this is where it switches from concave up to concave down. So this curve is a little more flat than this one, which also has still a mean of 3.5, but the standard deviation is now 0.7, which means my inflection points are 2.8 and 4.2. So they're closer together, so my curve gets squished into the middle. And this is because the area under the curve is 1, okay, no matter what. So so you can see that when you make the standard deviation smaller, your graph just becomes more vertical, okay? And make the standard deviation bigger, it'll kind of flatten it out more. All right, and so here it's showing us the same thing. The standard deviation is 0.7, but now we moved the mean to 1.5. And you can see all that does, these graphs look identical, except this one, the mean is 3.5, and this one, it's 1.5. So the mean tells us the location of the curve, and the standard deviation tells us what, like how wide the curve is. So we need both of them. All right, so a standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1. So the mean is 0 and the standard deviation is 1, which means mu minus sigma is -1, mu minus 2 sigma is 0 minus 2 or -2, mu minus 3 sigma is 0 minus 3, right? And same way up here, mu plus sigma is 1, mu plus 2 sigma is 2, mu plus 3 sigma is 0 plus 3 or 3. And so you notice they called this a Z because these correspond to Z-scores. If we take our value minus the mean and divide by the standard deviation, we get a Z-score. So if our X value is actually the mean, the Z-score will be 0. If our X value was 1 standard deviation above the mean, the Z-score would be 1. So when we use the standard normal distribution, we also call it a Z distribution because any value from any regular normal distribution with mu and sigma can be transformed into a Z-score using X minus mu over sigma. And we end up with that we can basically transpose any value of X onto a standard normal curve and get a Z curve instead. And the reason that this is important is before we had computers and fancy calculators to do the calculation for us, because even scientific calculators have these built in. But before we had those, we would have to use tables to do the calculations. So I'm going to show you how to use the table, but today we have technology that will do the calculations for us. But before we had that technology, because there are so many values for these tables, there was only a table created for the standard normal distribution, and then you would transform your distribution into a standard normal so that you could look up values in the table. Okay, so this is what I was talking about, transforming the values. So each data value of a normal distribution for random variable X. So here's our regular normal distribution. We have our mean, mu, and we have we know what the standard deviation is, sigma. And again, this is the inflection point, would be about here, mu minus sigma, mu plus sigma. And then these are the values that X can take all along here along the X axis. Okay, so these are the values the random variable X can take. And we can transform this entire distribution, all the possible values of X. We can calculate a Z-score for every one of them and transform this using Z equals X minus mu over sigma into a standard normal distribution with mean 0 and standard deviation 1. And then we can use the standard normal table to find the cumulative area under the standard normal curve. And what this is giving us is the percentile, the cumulative area under the curve. So if I draw a line here, okay, so let's say I pick the point that's 1 standard deviation above the mean, the inflection point, and we know the value for X based on what the mean and the standard deviation are. So let's use my original example. The mean is 100, the standard deviation is 10. So my X value is 110, that's here. I can calculate what percentile X is by using the area from here up to here. The cumulative area gives me the percentile. And since that X corresponds to a Z-score of 1, I can look it up in the standard normal table, looking up a Z-score of 1, and it'll give me back what the table will tell me is the area here, or what percentile 1 standard deviation above the mean is. So some properties. The cumulative area is close to 0 when we get to Z-scores below negative 3.49 or above positive 3. The cumulative area is close to 0 below negative 3.49. So once we go past 3.5 standard deviations below the mean, even though this never touches the axis, that the area of everything beyond this, so all of those numbers added up, is really close to 0. And it's the same thing out here. The area under the curve out here is also close to 0. So the other thing that'll happen is if we look at the cumulative distribution for Z equals 3.49, it's basically 1. Okay, and then the middle, the cumulative area for Z equals 0, since Z equals 0 is the mean, it's not close, it actually is 0.5. So that's because this is the mean is the median. So half of the area under the curve is here and half is here, because remember the median is the 50th percentile. So for z equals 0, the cumulative area is 0.5, and that also corresponds to the probability that z is less than or equal to 0 is 0.5. And then the cumulative area is close to 1 for z equals 3.49. So basically everything out here is almost 0. So once we get to about 3.5, we pretty much have all of the possible values that the variable can take. Right, so the way that we find the area under the standard normal curve is we're going to sketch the standard normal curve and shade the area under the curve that we're looking for. So to find the area to the left of z, find the area that corresponds to z in the standard normal table. So the area to the left of z equals 1.23 is 0.8907, and we use the table to find the area. I'm going to come back and show you guys how to do this using both the table and using Excel after I finish going through the slides. And then if I want to find the area to the right of the curve, I can't find this using the table. Okay, so what I'm going to do is I'm going to look up the area to the left of 1.23, which we already knew from here, right? That's 0.8907. And then the area to the right is going to be 1 minus that, because the whole area is 1. So to get the area to the right of z equals 1.23, I use 1 minus 0.8907. And then to find the area in between two of them, I'm going to start with, so we already have the area less than 1.23, and that's 0.8907. So this part plus this part plus this part is 0.8907. And then I can look up in the table, what's the area to the left of negative 0.75? And when I look that up, I get 0.2266. So this area here is 0.2266. This plus this is 0.8907. So it's showing you these two added together is 0.8907. So if I take 0.8907 and subtract off the 0.2266, that gives me this area here in the middle. Okay, and I'll show you how to do that using both the tables and using Excel. So that's the end of the overheads. All right, I'm going to leave this up and I'm going to show you guys how to look this up in the table. So first, let's start with the table. I'm going to copy this because I want to go to the textbook. I'm just going to copy this so I can open up a new tab without going back through Canvas. Okay, so I am going to open up our textbook, and the Z tables are in the appendices of the textbook, and they are in Appendix 4. So let's go ahead and open up our textbook. And then if we click on the table of contents, we can go to the appendices. Okay, and it's in Appendix, I think it's in Appendix B. Okay, so table 4 is the standard normal distribution. So this is the one we want. So again, I went to Appendix B, table 4, right? So this is where we find it. So this is the standard normal distribution table. Okay, so you can, I recommend you download a copy, keep it somewhere where if you want to use it, but you can also, I'll also show you how to do this in Excel. All right, so let's go back to our slides and let's look. Okay, so the first one that they did was, make that a little bigger. So we're looking up, so let's start with when Z is 0. So this table is split up into two parts, the negative Z scores and then the positive Z scores, and zeros in both of them. So the way the way the table works is this is the Z value. It uses two parts, this part and this one. So it gives you the Z score to 2 decimal places. So a z-score of negative 3.49 is 0.0002. So that means that the area to the left of negative 3.49 is 0.002. So this gives you negative 3.49, and this one gives you negative 3.40. This gives you negative 3.39, 3.38, 3.37, down to 3.30. So to get the second decimal place, that's why they draw the table like this. So you can see why we wouldn't want to have a table for every possible mean. Okay, so it's easier to convert to a z-score. All right, so the first one I wanted to look up is actually 0. So remember, this side is 0.9, the side over here is 0. So 0.00 is right here, and it is 0.5. And then if I go to the next page of the table, usually a little thing pops up here at the bottom so I can go down. I can go up, there we go. The arrow wasn't showing up for me. This shows me confidence levels. We do this in the next chapter, so we're going to skip this part for now. And I don't know why it puts these in between. And then here is the positive part of the table. So now we have positive z-scores. And notice these do the opposite, just kind of the way the table flows. So this one is 0.00, 0.01, 0.02, 0.09, 0.20, 0.21, 0.22, 0.29, and so on. So again, this is 0.5. 0.00 is 0.5. So the first one they wanted us to actually look up, though, was z equals 1.23. So we go z equals 1.2. So I need this row here, 1.2. 1.20, 1.21, 1.22, 1.23, 0.8907, 0.8907. So that's how they got that value. And then this next one, and then the area to the right, again, we just take 1 minus to get the area to the right. And then to get this area in the middle, I already had the 0.8907, and then I need z equals negative 0.75. So we would go up to the negative part of the table. And then I go negative 0.7, 0.7, this is 98765, 2266, 0.2266. So that's where they got that from, using the Z table. Okay, so let's also look at how do we get that using Excel. So let me go here and open up Excel. Okay, and let's go to, all right, I'm just going to create a new tab for the normal distribution. Okay, and I'm going to call this chapter 5. Okay, so the way that we would look this up, so if I go to back to my table here, and I want to look up when Z is 1.23. So what I want to do in Excel is I want to create this so it'll find the probability for me. So we want to put in a Z, right? And then we want to spit out the probability that that we get a value. So I'm going to call this big Z is less than or equal to that Z-score. So I want the probability that I get a value less than or equal to whatever this Z is. So this is going to be our input 1.23. Okay, so I'm going to go ahead and make that red. All right, and then for my probability, I'm going to go equal norm. It's norm.dist. This one is for a normal distribution for a specified mean and standard deviation. This is an inverse normal, and this is the one I want because I want it for a standard normal, so for a z. So I want norm.s.dist. So I'm going to grab that, and all I need is the z-score, and cumulative should always be true. Okay, I don't know what it spits out when you say cumulative is false, because there is no such thing as an exact value for a continuous distribution. So we just want to make this true. So again, it's z and then true. Okay, and this will give us that 0.8906, exactly like we had before. So again, this is my z that I put in, and then this spits out my probability. And this is the area to the left of z. Okay, actually, why don't I call it that? Because we didn't cover probabilities yet. I will call this the area to the left of z. So to get the area to the left of z, you're going to use norm.dist, the z value, and true. Okay. Oh, I need to make this bigger so you guys can see what I'm doing. Sorry. Okay, so to get the area to the left of this z value, you're going to put in the z value, and this is for the standard. And I'll even move this up. Okay, so the area to the left of z, we use norm.s.dist. And then if we wanted the area to the right, then it's just going to be equals 1 minus the area to the left. Shoot. I'm trying to just copy this. Let me try one more time. I just wanted to copy my formula so you guys can see it. Okay. Here we go. So this one is norm.s.dist, this value, comma, true. And this one is just 1 minus the value that we got that was to the left. That's how we get the area to the right. And then if I want the area between two of them, so let's put in, I'm going to call them Z1, and I'm going to put in 1.23. And then I'm going to put in Z2, and that one's going to be minus 0.7. Let me copy this. Doing that just so I don't have to change it to red. Minus 0.75. And now I can do the area to the left of z. Right, so that's the area to the left of z1. And this one should be B6. So same way we did that, norm.s.dist, the z1, comma, true. And then I want the area to the left of z2. Okay, and I'm just going to copy this. Okay, and that one was my area to the left of Z2. And that's the 0.2266. And then the area between Z1 and Z2. And this is just this area minus this area. So this is how we would find those areas using Excel. right? So let's go back over here and look. So again, that area between the two was 0.6641, and that should match what we got when we did our calculation. All right, so let's look at our homework. And from what we just covered, you should be able to do your homework problems number 1 through 4. So this is Unit 3, Assignment 2, numbers 1 through 4. All right. So the first one talks about just which is greater, the mean or the median. That's from the text. How can you transform a standard normal or a non-standard normal distribution to a standard normal distribution? So let me go back in here to my, to my text. And remember to transform, we're going to use this. Z equals X minus mu over sigma. I thought I had a snipping open. You just add that to my Excel file. Z equals X minus mu divided by sigma. Okay, and then this one, it just asks you, is this a normal distribution? I'm gonna let you guys answer that on your own. And then here it wants you to find this area. So it tells you here you can use the normal tables, or we can now use what we've set up in Excel because we already set this up in Excel. So remember, I always recommend that here's our template. So I'm going to call this chapter 5. But I could go in and change this template. Okay, and then I recommend that you copy this. So if you right click here, you can go move or copy sheet. You can create a copy. And we want to put it before, so I want to put it after this sheet. So I'm going to put it here. So it puts it next to here. And then this one can be your chapter 5 homework. And this way you won't mess up your template. Okay, so now you can just go into this one and put in the values. So they're asking us for the area between two values. And notice I have the larger one first. So I just want to put them in the same order, 1.36 and 0. Okay, if I switch the order, it'll just give me a negative answer. And now it calculated the area to the left of this. The area to the left of this is 0.5. I subtract them and I get 0.41309. So the area, or the area corresponds to the probability. So the probability that Z is between 0 and 1.36 is 0.4131. Okay, and it always wants it to 4 decimal places because that's what the tables give you. All right, so I wanted to just show you if I switch the order here and do them backwards. What it's going to do is give me a negative probability, and that's not possible. So it gave me the same answer, but it made it negative. Okay, so make sure that you put them in the right order. So this one should be the bigger one, and this one should be the smaller one, because that's how my example was. All right, so that is the end of section 5.1. Stay tuned for section 5.2.